Good afternoon. Actually, I'm kind of here on a little bit of a false pretenses because although I'm going to be talking about Elixir, what I'm really talking about is something slightly different. I'm really going to be talking about how changing the way, or changing the language that you use can actually change the way you think about programming. In fact, think about anything. So let me just start with an introduction. I have been programming for, tomorrow's my birthday. And so if you kind of like count it birthday to birthday, I've been programming for 43 years, which I'm not even going to ask people to put up your hands if you're less than 43-year-olds, because I just hate you anyway, right? So I've been programming a whole lot of time, and I'm an expert in all sorts of things, and you know, I'm just absolutely the person. Oh, all right. So yeah, I'm an old fart, right? Why should you listen to me? Well, one thing is that us old farts get stuck in our ways, right? We tend to latch onto something that works, and we'll stick with it because, after all, it works. It depends on the generation you are as to what works or what doesn't work. But there'll always be those things that just are absolutely perfect for you. The thing I've observed, though, is it's not just us old farts that get stuck. Young ones do, too. And one of my examples of that right now is object orientation, where people are saying, sort of, OO is the only way to write code, and we have languages like Ruby and JavaScript and Java or anything else. OO is the way to write code, and that's clearly been the case because for my entire lifetime, that's how people have written code. So what I want to try and do is to try and break you out of that just a little bit. So why do we want to get out of this? Well, one of the problems is that it's really easy to get comfortable. Now, when I say comfortable, it's relative. I mean, we're sitting in an industry where change is a given, where change is unbelievably fast. I don't think any other industry changes at quite the rate we are changing. And I mean, that's scary. And it's hard. It's hard to keep up, it's hard to keep current, and it's hard to be productive. So when we find something that seems to work, we try and latch onto that as a fixed point in the midst of all the rest of the chaos that's going on around us. And so we'll get comfortable with those fixed points until someone bumps us off onto another fixed point. But when we do that, we get lazy. And we stop looking into that particular area. We make assumptions. Object orientation, that's the only way to do things. Classes, that's the only way to design systems. Unix, that's the only platform to deploy onto. Whatever it might be, we have these assumptions, and then we just get lazy with them. There is another sort of synonym for lazy in this context, and that's maintenance programmer. Right? People who don't change are not going to be doing exciting things 5 years from now, 10 years from now. Now, there's money in that. People are still making decent change, maintaining COBOL programs. But I don't necessarily think that's what you want to do with your lives. So I think there's good reason for us to move out of that comfort zone. Now, I'm talking about this because I got lazy. I've been doing Ruby now since '98, I guess. So that's coming up on 20 years. And pretty much all of my programming life during that time has been Ruby. Now, there's a bit of JavaScript, but by and large, it's been Ruby. And that's great, because I'm really good at Ruby. I can code Ruby without even thinking about it. The way you can drive a car and get somewhere and not actually remember driving? Yeah? Well, that's because your brain has gone through this process of making something implicit in your head. There's actually a triangle of learning called the Dreyfus model. And it's all about taking external stuff and moving it internal. So it becomes like below the level of conscious thought. And when you first learn to drive, right, it's white knuckles, no one can talk to you, right? I mean, even just like, switching the air conditioning on or off is like a major exercise because you've got to take your hand off the wheel and stuff. It's scary. But as you get better at it, you just start to code fluently and naturally. And that's because it's become internalized. And that's the same here. You know, I've been programming Ruby so long, literally I can write, or I have been writing code, and don't actually remember writing it, which is kind of freaky. But all along that time, I was looking for a language that would help me move away and help me move into the functional world. Because I strongly believe that it's really almost impossible to debate this, right? The future is definitely concurrent, and I think most people would recognize the future is functional. So that's the world we're going to live in, and I was looking for a language that would let me, A, get into it myself, and B, help other people get into it. And I looked at a bunch of languages, and I never really found something that gave me that kind of feeling that Ruby gave me. Right? Ruby is a fun language. It's a good language. It makes me feel good to write it, right? And I was looking for another language like this. And I was talking to Corey Haynes, and I were doing a course together. We were giving a course. And over breakfast, I was like, you know, complaining that I couldn't find that language. And he said, have you had a look at Elixir? Now, I had a look at Elixir, about a year previously. And it was all right, but I wasn't too impressed. But when I got back that night, I downloaded Elixir, and it felt exactly the same as the first time I downloaded Ruby. That I brought it up, got it into an interactive shell, and before I knew it, 8 hours had passed. Which meant I was lousy the next day giving my course, but I knew I'd found something that I liked. So, why do I like Elixir so much? I like Elixir because for the first time, for a long time, I'm feeling challenged. I'm feeling challenged about all the old ways I thought about programming, all the old ways I thought about organizing applications. Right? It's different. And it's actually hard for an old fart to change like that. But I'm working on it. So I really honestly think that programming in Elixir has changed the way I think about programming. I'm aware of that. If I go back to program Ruby now, I program Ruby in a different way because of it. So I need a little token appeal to authority here, just to kind of make sure that everybody believes this is actually real. And I can't think of anything more serious here than Ludwig Wittgenstein, the philosopher, who, by the way, looks really sad because he failed to get the part in Eraserhead. But he wrote really almost nothing. He wrote a 65-page pamphlet. He wrote a couple of papers, and apparently he wrote something for children. I can't imagine. I got to show you this just because it is so cool. In the introduction to his one book, he writes, "How far my efforts agree with those of other philosophers, I will not decide. Indeed, what I have written here makes no claim to novelty in points of detail, and therefore I give no sources, because it is indifferent to me whether what I have thought has already been thought before me by another." This man is a programmer. Anyway, one of the more famous quotes out of the books, "The limits of my language are the limits of my world." And he actually goes on to say, or to quote, to prove, that if you cannot express it, then it doesn't exist. There's a kind of trivial proof of that, and that is, if you can think of something that exists that you can't express, tell me what it is. See the thing? See? Clever, right? Anyway. And I actually believe that. There's a whole lot of work that's been done on this. The famous work was done independently by two people, Sapir and Worf, back, I guess, in the 30s. And they came up with this hypothesis that basically says language changes the way you think. And that was like really cool, and everybody liked it. During the 60s, it fell out of favor, because it was kind of like saying that people that had different languages were somehow less capable than other people. But it's actually coming back into favor, but in a slightly different way. And if this works, which is always debatable, here's a little bit of a BBC documentary about a people called the Himba people.
Northern Namibia.
Oh, I'm not getting sound. Hang on a second. Let me see if I can. There we go.
Northern Namibia. Home to a remarkable tribe, the Himba.
What is the color of water?
Buru, which includes some greens and blues. And Dumbu, which includes different greens, but also reds and browns.
Color, which one?
He's testing how long it takes them to spot a color which is different from the others.
Now. Can you do the same thing again?
This is what they're looking at. For us, it's quite hard to spot the odd one out.
Okay, can you point one more time towards the different color? Very good.
But for the Himba, it's easy to see the green which is different. The next experiment is trickier for the Himba. In this one, they're shown a circle of green squares, which includes one blue square. For us, we have separate words for green and blue. But as the Himba have the same word for both, it takes them longer to spot the blue.
Is that amazing? Right? I mean, that to us, that blue jumps out. It's hard for them to see. Whereas for us, that green looks just like all the other greens. And yet to them, it jumps out. The wildest thing is, gave this talk in Melbourne. Afterwards, somebody came up with me, held out their cell phone, and there was a picture of that woman. He'd actually been to that village the previous year and had met that woman, which was kind of wild. So, why does this work? Well, no one's too sure, but they've been using lots of functional MRIs and stuff like this. And it turns out that this effect only really works if the difference is in your right field of vision. And the reason is the right field of vision is actually transferred across to the left-hand side of your brain, where also a whole bunch of your speech stuff is. And there's a theory that there's some kind of cross-correlation between that and vision. If you look at it from the left field of view, you don't get that confusion. There are other things that prove this, things like the Stroop effect, where you have words written, like you'll have the word blue, but it'll actually be colored red. And then you'll have yellow, and it'll be colored green. And what you have to do is to say what color it is and not what word it is. And nobody can do that fast, right? Everybody trips up because you can't stop yourself reading the words. So there's clearly some interaction there. So what has this meant for me personally? Well, Elixir as a programming language is kind of a little bit Ruby-like in terms of syntax. It runs on top of the Erlang virtual machine, Beam. And if you haven't used Erlang, it is used probably to switch the majority of like text messages in Europe. I don't know what it's probably down here as well. It's pretty much universal. It's used in telephone exchanges and switches. It's fundamentally a highly concurrent, highly resilient language. Written correctly, Erlang applications have 9 nines availability. And part of the reason for that is the virtual machine also supports the hot swapping of code on a per module basis, including the migration of that module's data to a new format if necessary. So it's a very nice, well-tested environment. Erlang's been around since the mid-'80s, and people have been deploying Erlang code for large, large applications ever since. So it's a functional language, not as functional as a language like Haskell, but it's a functional language. It's a concurrent language, as I say. It's pragmatic. For example, when I say it's functional, you don't have to do things like worry about using I/O if it has side effects and this kind of stuff. It's kind of like functional, but common sense functional. And I personally find it to be fun. There's all sorts of cool things you can do with Elixir. For example, it's homoiconic, which means the intermediate form of a compiled Elixir is actually Elixir data structures. And that means the macro system can manipulate code directly, right? It's all just Elixir. So it's got a very nice, very powerful macro system. And in fact, most of the control structures in Elixir are written in Elixir. So, I mean, it's a Lisp in that kind of way. Not a real Lisp, but getting there. But it's different, and it's different enough to make you think differently. So I want to show you how Elixir has worked for me. Two things I want to look at is pattern matching and the fact, and the obvious fact, really, that it's all about transforming data. So let's look first at pattern matching. Now, normally when I give this talk, I have like 6 or 8 slides that talk about pattern matching, but everybody said to me, Australian audiences are smart, and I just want, the facts. So here's the one slide that condenses all of those things. In Elixir, an equal sign is not assignment. Instead, it's an instruction to the compiler, or the runtime, I guess, to say, make these two sides equal. It's way more like the algebra that you learned in school. Right? Because in school, if you say x equals 1, you're not assigning 1 to x, you're just saying the two are the same thing. And that's what we're doing here. So after doing a equals sign 1, then the runtime is going to bind a to the value 1, simply because that's how that makes it true. Right? Having said that, well, once I've said a equals 1, it would then be perfectly valid to say 1 equals a, because that's also true. We have here we have a tuple of 2 elements, and on the right-hand side, those 2 elements are 2 and 3. So to make that match, or the only way to make it match, the runtime binds 2 to C and 3 to D. And the same thing applies on the next line there to lists. Elixir strings work the same kind of way. So the little spaceship operator there is string concatenation. So I'm saying on the left-hand side that a string Elixir concatenated to something should be the same as Elixir rocks. And the only way to make that happen is to make rest the same as rocks, the string. And then last but by no means least, I can deal with variable length lists by separating out the head and then the rest of the list. So here I'm doing a pattern match on the list 1, 2, 3, 4, 5, 6. And I'm saying the variable head is going to get bound to the head of the list, that's 1. And the variable tail is going to get bound to the tail of the list, which is 2 to 6. And that will match any list of length 1 or greater. It will not match an empty list, because there's no head. Pattern matching is not just used in those equal signs. So here's an example of using pattern matching in a case statement. So file.open returns a tuple. And if the first element of that tuple is the symbol OK, then the second element is the device that you can read from. If the first element is instead the error symbol, then the next element is the reason code that it failed. So here I can match on this. You'll notice that the match on the left-hand side has 1 constant and 1 variable. So here the constant, which is the symbol OK, means that this will only match if file open returns a tuple that starts with OK. And then whatever is in the second thing gets bound to that device variable, which I can then use on the right-hand side to read from that device. Pattern matching also applies to functions. So here's an anonymous function in Elixir. It's a single function, but it actually contains 2 function heads. So if you like, function signatures. So the first line is the function, if you call it with 3 parameters, the first one is the symbol plus, then A and B, whatever they may be, I'm going to return A plus B. If instead I call it with the first symbol times, then I'm going to multiply the next 2 parameters. So you can see I can call it there with 3 and 4 and get either 7 or 12. That's an anonymous function. I can do the same thing with a named function. So here I'm pattern matching. This is, somewhat confusingly, this is one function definition that, again, has two heads. And one of the things the Erlang runtime does is it optimizes the crap out of these, right? It's actually, to give you an example, Elixir supports UTF-8. And whenever you support Unicode, you have to have a massive big lookup table that's going to map things and tell you about combining characters and all this kind of stuff. And typically, people actually implement that as some kind of hash, a dictionary, so they can look it up based on character codes and things. In Elixir, it's actually compiled into tens of thousands of function heads, each with the same name, but with different parameters. And they did tests, and that's actually more efficient than doing any other data structure, because the Erlang runtime optimizes it so much, which is pretty cool. So, pattern matching matches on shape and on content. You can do destructuring, like when you have the tuple with C and D in it. You can destructure to get the individual elements out. And it's recursive, so I can nest things inside things and then do matching on those. So it's pretty cool. So I'm using these instead of conditional logic inside my functions nowadays. So just to give you the world's most boring example, all right? This is the one everybody did. The only interesting thing about Fibonacci is whether fib0 is 0 or 1, all right? And that's like a big controversy, and we can all fight about that afterwards. But let's assume it's 0. So there's the definition of Fibonacci. You'd get that in Wikipedia, anywhere you look up Fibonacci. It will look just like that. What's the Elixir implementation of that? It looks like that. Yeah, fib0 is 0, fib1 is 1, fib-n is fib-n minus 1 plus fib-n minus 2. Let's ignore the fact this is horrendously inefficient. I just wanted to make a point. Okay? So the key thing here is, I mean, it speaks for itself, really. The program, the structure of the program reflects the specification that you're implementing. And then slightly more subtly, the implementation reflects the transformation that you're trying to achieve. And those two things together are the code that does what you want. And it took me a long time when I started coding this way to work out that I'm really not interested in state. I'm really interested in transforming state. And once I worked that out, it got a lot easier. And part of that is because my language for the last 25 years has been object-oriented. And so I'm blinded by this idea that state is king, right? Objects maintain state. And the reality is, state doesn't do anything, right? If you had a choice between a program that was really, really good at holding state and a program that was really, really good at transforming stuff, which is the one that gives you business value, right? You've got to do a transformation to get value. So I'm really learning something here with these programs. Let's look at a few more examples. Okay, again, these aren't necessarily the way you'd implement them in the real world, but they illustrate the point. Length of a list, the specification is the length of an empty list is 0, the length of any other list is 1 plus the length of the rest of the list. And if we look at the implementation in Elixir, we get something like this. Okay, pretty straightforward, pretty boring. Similarly for map. Map is slightly different. So map goes through a list and applies a function to each element in that list. So the implementation of map looks like this. I'm going to map, if I have an empty list, I return the empty list. Otherwise, if I map a list that has a head and a tail, my result is going to be the result of calling the function on the head concatenated to the map of the tail. So let's look at something just a little bit more practical. Not much, but a little. Maybe we got the job of doing some run length encoding to compress down a string of values, or a list of values, sorry. So in run length encoding, I look for sequences that have the same value, and I'm going to replace those with just one copy of that value and a count. So here in my list, I have 1 and then 3 2s. So I'm going to replace that with 2, 3 as a tuple. Then I have a 3. I have 2 4s, so I have 4 2, 5, and 6 4, right? So that works, or one way of implementing that would work something like this. I have my input list, and I have my result. And I'm going to look at my input list at the very start of my input list and see what to do. So in this case, that 1 stands on its own, so I'm just going to copy that straight down to my output. Now I'm looking at the input list, and I see that I have 2 2s. So I know I have some duplication here, so I'm going to replace those 2 2s with a tuple, 2 and then a count of 2. Now I'm looking at my input list and saying that the first element is a 2 repeated twice, and the next element is a 2. So I can replace that with 2 3. Now I can't do anything else with that, so I'm going to move that down to my output list. Now I'm looking at a 3, nothing special, so I move that down. Now I have a 4. Oh, look, there's 2 of them, so I'm going to replace that with 4 2. Then I'm going to copy it down, etc., etc. So if you are a Java or a Ruby or a conventional programming language programmer, I want you to think just for a second about how you would implement this. And think about the various edge cases that you have to deal with. First element of the list is part of a sequence. The last element of the list is part of a sequence. Sequences of length 2, sequences of length greater than 2. All of those kind of things that you have to think about. There's quite a few little edge cases. And when I was preparing for this talk, I actually coded this thing up in Ruby, and sure enough, I got bitten by one edge case, which was, when the list ends on a sequence. And I had to go through and fix that. How would you implement that using pattern matching? So in a functional language, whenever you need to generate a result, you're going to have some kind of, well, typically, you're going to have some kind of additional variable that you're going to stick that into, or value. So in this case, I'm going to have a helper method. My external API is encode, and I give it a list, and I'm going to call helper method underscore encode, to which I pass that list and my empty output array. Okay? So if you like thinking in things in terms of invariance, then you can say that the concatenation of list and the output array is going to be the same logically as the original list, but it may include some compression. So the easiest case to deal with is when we just have some arbitrary element at the start of the list, here A, and a tail. All we're going to do is put that tail at the front of the result, and then call ourselves again, sorry, put that element A at the front of the result, and then call ourselves again with tail. Yeah? So with just this code and one extra thing, this will basically copy the input to the output. All right? And there's an edge condition we have to deal with, but we'll do that in a second. Now we have to look at the cases of compression. One case of compression is if that list, oh, actually, I've done this the wrong way around. Let me do it the other way around. If the list starts with 2 of the same value, okay? So that A, during a pattern match, is going to get bound to, for example, 3, yeah? If the second value, in order for it to match, it also has to be a 3, because it's the same A, yeah? So if my list starts with 2 elements of the same value, and then has the rest of the tail, I am going to replace that input with a tuple of A, and then the count 2, and then just call myself again. The next phrase here deals with the case where the head of my list is that tuple, representing A and a count. And then if the next element in the list is also an A, then I'm going to take it out of the list and update my count, so I replace n by n plus 1. And then finally, if I have an empty list, I'm done. Yep, so I've taken all the things out of my list. I'm now done. And just because I'm building up that output list, moving things to the head of it, I actually have to reverse it to get it out. And that's a very common pattern in Elixir, and reverse is really fast, so you don't have to worry about it too much. So that's the code that does this run length encoding. And this code, when I wrote it, worked first time. Because I can see each of the conditions, each of the states, and it just kind of like falls out. And it's also easy to imagine changes to it. So if I said to you, we'll only run length encode 3 or more, yeah, you can see what change to make. It's easier to test, because each of these cases is broken out into a separate thing that I could test if I needed to. So that's pretty cool. But if you look at that, you'll say, there's a whole bunch of duplication in there. I don't like that. Can we fix that? And the answer is yes, we can fix that. Because what we're really doing, if we just like extract out the transformations, if the input is empty, then we're done. The result is the values. If the input contains 2 of the same thing, then we're going to replace it with that, and we carry on with the same result. If the input has a tuple, and the next thing is the same as the head of the tuple, then we'll replace it. Otherwise, we copy the head of the input to the result. That's what our program does. And we have this thing called input and new input. But we could replace those words with state and new state. And then what we have is a state machine, where we're triggered by the next element on our input list, and we use that and the state to work out what to do next. Now, whenever you say state machine, people think, oh, that's cool, because my language has a library for doing state machines. You know, if you're a Rails developer, you may have used Access State Machine, you know, or whatever. There's always like a library. Well, I'm here to tell you that anybody that uses a library for a state machine is a fool. Because, I mean, in any language, you can just use a hash. In a functional language, though, there's actually a state machine built into the library, and it's called reduce. All right? So reduce basically takes something that's enumerable and applies it to a function, and at the same time passes an accumulator value to that function. And what that function does is take the element from the list and the accumulator and returns a new value for the accumulator. So in this case, our reduce is our state machine, and we're passing into it the list and an empty list, which is our output. And we're going to call encode, which is our function, which implements the state machine. And then all the rules for our state machine are simply here in this case statement. So I'm going to look at the list and the result, and that table there is identical to that table I showed you on the previous slide. So we've taken a whole bunch of code and reduced it down to a simple set of rules. Right? Those 3 lines there are all that's needed. And in fact, the rest of it is boilerplate. So if I want to run a state machine against any enumerable object, that top thing there will do it. And then I just have to write my little cases down the bottom there. It's a really super way to code. It's a really nice, easy way to look at coding. And it's so much easier to work with. Now, this isn't new. I mean, we've had decision tables, state machines since the 60s, you know, this kind of stuff. We've had Blackboard systems that do roughly the same kind of thing. This isn't new. But I've not seen anybody talk about the functional side of the world as being a set of transformations built into state machines. Right, so functional transformations built in to state machines based on pattern matching. So in our run length encoding example, we have our transformation there, it's reduce. We have our event plus the state. And then we have our transitions. Nice and simple. Let me give you just a couple more examples. One of the things I do when I come across a language I like is I play with it. Right? And I'll play with it by running through a typical set of exercises. And if I really, really like it and I want to commit the time, my last exercise is to write a Markdown parser in that language. And the reason is that Markdown is phenomenally ugly. I mean, it really is ugly. It's totally unspecified as to how all the edge conditions work. And it's really difficult to actually come up with something regular that actually will parse it. So here's an example of Markdown. And the lines with the underscores or the hyphens or the equal signs are headings. So system and types is actually a top-level heading, and then IDs and ports is actually a second-level heading. This is actually some of the source code from the Elixir book. And in my Markdown parser, I actually have two separate state machines, one of which goes through and breaks my input up into tokens based on the lines. And then the second one is something that takes the lines and converts them into logical structures. So here, for example, the rule is that a blank line, followed by a line of text, followed by a line of underscores or equal signs, is a heading. And the code that actually does that in my state machine looks like this. So if I'm parsing, and my input at the current point contains a blank line, a line of text, and then the ctext underlines, which is those equal signs and minus signs, followed by the rest of the input, then I'm going to replace it with a construct that represents a heading, and then the rest of the list. So it's really easy. I mean, it's ridiculously easy. So I've added new features to this by just adding additional state transitions. And I've been blown away that they actually work. Right? In every other Markdown parser I've written, there's always been interactions between things. In this one, it just falls out. It just works. It's fantastic. You can take this, I think, and make it large scale as well. So, for example, say that we were writing some kind of REST service. And we're handling something like, I don't know, a Groupon or a Living Social, where we have special offers that we want to offer our customers. And some of those special offers are local, local shops. Some of them are national, sort of like, just like an Amazon-y kind of thing. And we want to go and fetch the offers that are for this particular customer and combine them together and respond back, showing them a nice page with all their offers. And we would very much like to make those two things asynchronous. Now, I know that we could, go and use Flux or, some kind of reactive approach to this, or, we could spend our entire week picking the libraries that we're going to use to do this. But we don't need to, because we can represent this as a simple Petri net. And if we do that, we can represent it as a state machine. So the code looks something like this. We're going to go look up our user. Then in parallel, we're going to go find the local and remote offers. And then we're going to format a response once both of those guys have come back. If either of those guys come back with error, we're going to do something different. So remember that in the run length encoding, I had that method at the bottom that had the case statement in it. Well, the case statement for this whole program would look something like this. Initially, all my state has in it is that I want to get a get offers thing, and I have some kind of authentication token. So I'm going to transition that into a new state where I have the same get authors thing, but I'm adding a new field, user, and I'm going to go look that user up based on the authentication token. Now, if that fails, then my user from is going to return nil, in which case the next pattern is going to match. And I'm going to respond not authorized. Otherwise, if I've got the user, I'm going to send off two asynchronous requests, one for the local, one for the remote, and now I'm going to wait for them to come back to me. If either of them come back to me with an error, then I'm going to respond immediately with an error. But if both of them come back without error, now I can format my response and send it on. So, the point is that I think you can think of pattern matches as rules in a state machine. And each match then specifies the transition, which is a transformation of state of that machine. And that transformation is the application of functions. And it works really, really nicely and compactly in a functional language. And I think that gives us interesting opportunities, because it's easier to make parallel, you effectively come up with a DSL every time you write something, because that little state transition table is your DSL. And if you wanted to, you could actually take that a step further, and if you want to have like a more business level DSL, you could have something that generates that state transition table for you. It gives you some really nice reuse capabilities, because each thing is just a single transition, and each transition is pure, so therefore you can use that code anywhere you want. It's easier to test, because you can test it transition at a time. And I think you get better error handling. This is where I'm kind of like a little bit out on a limb. My experience has been so far that I can do better error handling, because I can say where in the states I am, and that will affect the kind of error messages I give. But I'm not too sure that's 100% the case. But I still think that by thinking about your coding a little bit differently, you can do some amazing things. Now, is this specific to Elixir? Absolutely not. You could do this same thing in any language. You'd have to do a little bit of work with tokenizing to get the state matching stuff done. But really, it's just, a lookup based on the current state and an event to generate the next state. Nothing special. But I would never have thought that this was really neat and tidy until I used a language that made it easy to express. And that comes back to the Himba. Right? If you have words to express it, if you have a syntax that lets you express it, then it's a lot easier to think about and a lot easier to come up with. So I think one of the things I would encourage everyone to do here, and I'm not touting Elixir, frankly, I don't give a damn what language you run. I really don't. But I really do want you to think about thinking differently. Explore new things. Try new languages, try new techniques. If you've not used a functional language, use a functional language. If you've not used a dynamic language, use a dynamic language. If you haven't used a static language, try using a statically typed language. Try new things, because each of those things will add to your vocabulary, add to your abilities, add to your experiences. So when you think differently, I want you to program differently. And then when you do that, please, don't just go and write a version of Rails in that language. Right? Let's not repeat yesterday's mistakes. Let's not rebuild yesterday's successes. But let's get out there and use these new ideas to create new things and move us all forward. And let's have fun. Thank you.